Hi, and welcome back to Codex. Today's speaker is Alex Cloninger from UC San Diego. Professor Cloninger is an expert in applied harmonic analysis, geometric data analysis, mathematical data science, and more. Today, he'll tell us about manifold learning. Take it away, Alex.
All right. Awesome. Thank you all for the invitation. Let me minimize that real quick. Okay. Today I'm going to talk about like a sort of research program that we've built up over the last few years about what we call bottom-up manifold learning and some of the guarantees and mathematical guarantees you can get about this. So before I jump in, I just want to give a quick highlight. So a lot of this work, most of this work was driven by my former student, Drew Foley, who's now a postdoc at Princeton. And he was co-advised by Gal Mishne, who's my colleague here in data science. And Dhruv is awesome. He's an incredible postdoc and will be on the faculty market in a couple of years. So please keep an eye out for him. I also want to shout out one of my additional collaborators, Sawyer Robertson, who is currently a grad student, but is on the postdoc market right now. Also amazing student. He contributed to a decent part of the beginning of the talk. So that's the thing. So what am I going to talk about today? I'm going to kind of give my boilerplate statement about manifold learning and what the setting normally is. So we always have high dimensional data, and if data was truly high dimensional with complicated functions, there's really all hope is lost, right? So one of the assumptions you can make often is that your data lies on or near some lower dimensional geometric structure. And so the question I'm really interested in is recovering that structure to some level of accuracy. And there are a few examples that I'll kind of go through, but just to demonstrate these are real settings, right? So you can have chemical, dynamics of molecules where all of the different atoms are kind of moving around in space. But what winds up happening is even though there's 24 different atoms, this actually winds up arcing out some sort of complicated three-dimensional structure in the way that they're allowed to co-evolve. And our goal is to learn things like that. And then my colleague Gal Mishne is a neuroscientist as well as a electrical engineer, as well as a mathematician, as well as an applied mathematician. She has a lot of hats. But one of the things I'm going to focus on here is going to be some of the neuroscience applications of like reading neurons from a monkey that is doing various tasks or a mouse that is doing various tasks and trying to recover the underlying geometry that's occurring inside of their neurons, right? So what is the world that they're seeing geometrically? So that's kind of the motivating applications. And so why do I call this bottom-up manifold learning? So a lot of the manifold learning a lot of people I think are familiar with is what I'm going to call top-down. So when I say top-down manifold learning, what I mean is we start with some global low-dimensional embedding. So this could be doing a random embedding. This could be doing some sort of graph spectral embedding, PCA embedding. The idea is you're trying to learn the entire global embedding at once, okay? And so, you have a Swiss roll and using Laplacian eigenmaps or something like that, you place into a low-dimensional space. And then there may be some type of refinement. For example, this is what happens with TSNE. This is what happens with UMAP, other algorithms that are trying to sort of find a better fit once after you've initially laid down the entire global. And I'd say most manifold learning techniques wind up falling into this setting. However, a lot of these techniques struggle because that initial embedding might be quite poor and could have what will often be the case is infinite distortion. It'll take 2 points that are far apart and place them in the exact same place on the embedding. Because of that, you're never going to be able to recover from it. So I want to think about a different setting where we instead think about bottom-up manifold. So what I mean by bottom-up is we start with our high-dimensional data and we just look at patches, right? You have a set of overlapping patches and you're just trying to find a good local estimate of what your data is doing. Okay, I'll define local rigorously in a minute. Once you have that, you're just going to lay all those down in your low dimensional space. Okay, and so I know that each local view is perfectly or very well embedded into my low dimensional space, but I've got potentially thousands of them. right? So what we're going to do is we're going to use the fact that these local views overlap with one another in order to do our refinement in that local space, or in that low dimensional space, okay? And so what that will hopefully give us is a guarantee where as long as our local embeddings are good, which we can give guarantees about, then as you align them, you won't wind up leading to a situation where 2 points far apart are shoved on top of each other, or 2 points that were incredibly close get ripped infinitely far apart, right? Because that's truly what the problem would be in any sort of manifold learning framework. So yeah, so there are examples of things that do this. There's like local tangent space alignment, a couple others. And then recently what we've been doing has been what we call LDLE, RATs, and then several other algorithms, which I'll kind of go into, okay? So the main questions that I want to focus on, and this is going to be kind of the outline of the talk, is first, how do we construct these local views such that they are low distortion, guaranteed low distortion? Okay. And in particular, I want them to be robust to noise. Once we have that, then the question is, how do we align these? What is the computational, what is the optimization algorithm we're running? How do we make sure we align them in a robust manner? Can we have guarantees that when we reach some minimum of our optimization scheme, we'll actually have a finite distortion embedded? And then finally, once we do this, how is that going to affect the downstream performance of data science problems, right? How's that going to affect us in a neuroscience problem, in a chemical molecular dynamics type problem? Okay, so that's kind of going to be the outline. I want to give a quick comment, which is that this talk and this sort of research is kind of a chicken and the egg problem. You could talk about how to deal with low distortion, local views, and just assume that I can align them. And then later I'll talk about how exactly I align them. Or I could talk about the alignment and you just have to trust me that the local views are good. And then I talk about how the local views are good. So just so you know, I'm going to start in this order, but I might wind up showing you a few global embeddings. Just trust that we'll get to exactly how we do that in a little bit. Okay. All right. So that's the setup. So we're going to start with local view construction. Okay. So one thing you can do is you could look at something like local PCA, right? So there's a lot of really great work on local PCA. Effectively, what you do is for every point, you take your k nearest neighbors and you project them into a low dimensional space via PCA just of that neighborhood, right? And those principal directions estimate your tangent space locally. The problem is when your data has noise, this can be severely corrupted, right? So why is this? Well, if you just imagine this manifold I have here on the left, simple, arcing back and forth sort of flower type thing. What I'm drawing here are basically the local tangents, local tangent vectors that you'd want, right? But when you add noise, when you're taking nearest neighbors and you look in a region of low SNR, like this region over here in red, locally, that thing basically just looks like a two-dimensional cloud, right? You're not able to discover the 1D structure there, right? So because of that, your PCA is just going to be two vectors in R2, right? And so you're going to have a really bad estimate of your tangent space in that region. In high SNR regions, like the green right here, maybe you'll do okay, right? So one might say, all right, well, what if I increase the size of my neighborhood? Well, as you increase the size of your neighborhood, now you're going to lose model accuracy, right? You might increase the size of your neighborhood so much that you're looking over a very nonlinear region. And then your PCA isn't going to do great just because, your data is actually curved in some way and you're trying to project it down onto a plane. So yeah, like I said, the key idea of this is that you want to choose your neighborhood size bigger than the scale of your noise and smaller than the curvature or reach of your data, right? And this can work, but when the noise level is hard, these things are all kind of intertwined, and it's not even guaranteed that there exists a neighborhood size between these two bounds, right? So that can be a little bit of a limitation. So what's our approach? So our approach is actually going to be to start with some global geometry. And then what we're going to do is we're going to use that to construct a local tangent space. All right. So how's that work? Well, first we just start with a graph Laplacian of our data, right? So you have points xi, you look at its nearest neighbors, and you build some kernel, say a Gaussian kernel. It doesn't have to be Gaussian, but something localized. And you build your random walk Laplacian accordingly. Okay. So there's obviously a lot of theory on random walk Laplacians, on manifold data. You can talk about how this converges to Laplace-Beltrami operators. You can talk about the first few eigenvectors are used for dimension reduction, right? But we're going to do something else, okay? So first off, let me just say very quickly, this was a previous work. One of the first things we did in this space was basically the observation that even if you have low dimensional data, say two-dimensional, intrinsically two-dimensional data, you can embed that data with two eigenvectors. But first off, it's not necessarily going to be the first two eigenvectors that you want, or the first two non-trivial eigenvectors you want. And also, it's not the case that the two eigenvectors you want over here in your data are the same as the two eigenvectors you want over here in your data. You might want different collections of eigenvectors to describe your data depending on where you are, right? Because the whole goal is basically just to find some sort of local, nearly orthogonal basis that you can use to describe your data locally, right? So what we did in our original paper of LDLE was basically choose for every point, or for every neighborhood, a specialized set of D eigenvectors. They're low frequency, but they're not necessarily the first column, okay? And used that as some sort of intrinsic coordinate system. So there's a whole paper about this. It's in JMLR, but I don't want to go into this because since then we have found a much better approach. So I'm just kind of tying this into things we did originally, but I want to talk about how we construct local views now, right? The key takeaway from this slide is basically it's not the first two eigenvectors you want. It's just there's a collection of low frequency eigenvectors, and you want to pick two out of that collection that are sort of the best you can create. So now what we've moved to is what we call it LEGO, Laplacian eigenvector gradient orthogonalization. And the reason we do this is because this actually works really well with noisy data. And when I say noisy data, what I mean is we assume we have some sort of submanifold, and then we're putting a tubular neighborhood around that manifold where that tubular neighborhood represents noise. This is a hard problem to recover the low dimensional structure because, I mean, in some sense, like in a differential geometric sense, there is no low dimensional structure, right? When you're at a very, very small neighborhood, the data is space-filled, right? So we want to recover that this is kind of the low dimensional structure and get rid of the noise, project all of the data from that tubular neighborhood back onto the submanifold, okay? So how do we do that? Well, here's the observation. So low frequency eigenfunctions that have a small eigenvalue of the Laplacian. These are actually very, very smooth. And they actually vary along the submanifold direction and not at all in the tubular direction, in the normal direction. So the set of low frequency eigenvectors of the Laplacian only vary in the submanifold direction and are constant in the normal direction, okay? Now, I am stating that. There are probably a lot of people in the room that know this as a heuristic, right? I promise you that in a few minutes, I will actually give you some theorems that we can prove to say, like, this is actually true, right? I'm not just stating this as a heuristic, okay? But for the moment, I want you to keep that in mind, right? Low frequency eigenvectors vary along the submanifold direction and are pretty much constant in the tubular direction, in the normal direction. So using that, I want to tell you our algorithm first, and then I'm going to motivate that heuristic that I just stated. Okay. So what's the algorithm? The algorithm is for every point, we're going to look at its neighbors, k nearest neighbors. Okay, so this is the point xj, and this is a collection of its neighbors. And we're also going to look at some eigenvector, low frequency eigenvector, and its representation at those neighbors. Okay. And now what we're going to do is we're going to try to estimate the gradient of that eigenfunction. okay? So why are we doing it, right? Well, if we can find the gradient of the eigenfunction, it's going to vary along the submanifold and not vary at all in the normal direction. So if we use that as our coordinate system, it's actually going to do a really good job to describe the local behavior of the submanifold. Okay? So how do we do this? Well, what we do is basically we run a mean square error to get a first order Taylor approximation, right? This is the actual variation of our function, of our eigenfunction. And we're going to say, all right, let's estimate that with some gradient where the gradient is the thing we want to estimate. Okay. How do we do that? Well, we say, well, the gradient is a smooth function, so it can be written as a collection of low frequency eigenfunctions. Okay. So this C is going to be really, really vital. What it's going to do is it's basically going to say, all right, using eigenfunctions, describe the gradient. Or sorry, one element of the gradient. You do this across all D elements, right? You describe that gradient as a function. And you can solve this via just a mean square error, least squares problem, pseudo inverses of these local neighborhoods, right? And then you stack them up. So for a given point xk, you look at the eigenvector, the gradient of the first eigenvector, the gradient of the second eigenvector, the gradient of the nth eigenvector. Okay. And the idea here is there's actually a ton of redundant information. Most of the gradients are varying along, if it's an intrinsically 1D problem, most of the gradients are all varying in the same direction, even if you're in very, very high dimensions. So what do? You take this collection of gradients and you just do a PCA of it. Keep the top D singular vectors. Okay. And those form an estimate of the orthogonal basis of the tangent space at xk. And you can just do that for every single point. Okay. So effectively all we're doing is local PCA. It's just that it's not local PCA of the original data. It's local PCA of the gradients of eigenvectors. Okay. So I will show you in a minute experiments try to argue that this algorithm works, that it gives you better estimates of the tangent space. But for a moment, I want to come back and actually talk about that assumption that I made, which is that the eigenfunctions actually vary smoothly in the submanifold direction and are constant in the normal direction. So we do this in two different ways. So I'm going to do one slide on each of these. There's an entire paper about this. I'll cite it in a minute. And I'm not going to lie, there's, this theorem in particular, I think has like 15 different sublemmas. So I don't want to go into the proof mechanism of all of this, but I want to kind of give the key notation and the key insight that we get out of this theory. So what I'm going to look at here is I'm going to assume I have that planted model, which is that I have a submanifold and I have a tubular neighborhood around that submanifold. Okay. And now what I'm going to measure are two quantities. The first quantity, EB, is going to be of some function, which in this case is going to be an eigenfunction, is going to be the variation along the manifold. Okay. It's the amount of energy that eigenfunction collects along the submanifold. And the other one, EB perp, is going to be basically the net gradient in the normal direction. So I'm basically trying to decompose whatever function I have into how its gradient varies in the manifold direction and how its gradient varies in the normal direction. And I want to measure the energy of these two quantities. Okay. And this is the main theorem that we can get out of this. If we have some eigenfunction of our tubular neighborhood, this is the manifold tubular neighborhood, then the eigenvalue of that eigenfunction actually has to satisfy two things. The first thing it has to satisfy is that it's lower bounded. And it's lower bounded by something involving epsilon r curvature to some power. This is just some constant. This is the key. Epsilon r to the -2. If you have a little bit of tubular noise, this is going to be an incredibly large quantity, right? times the energy in the normal direction. And then the eigenvalue also must satisfy that it's upper bounded by, again, some constants involving the tube, the curvature, blah, blah, blah. The energy in the normal direction, or sorry, the energy along the manifold, and some other factor that's very large times the energy in the normal direction. So this is not a perfect theory. I'm not claiming that this is like solved the problem of what happens when you have noisy manifolds. But what this says is the following. If your eigenfunction varies a lot in the normal direction, in other words, if EB perp is large or, decent size, then by definition, that eigenvector must have had a large eigenvalue. Okay. Now I'm only considering small eigenvalues. So effectively that eigenvector, if it varied a lot in the normal direction, I threw it out. I wasn't going to use it. Okay. And similarly, if the energy in the along the manifold is of a decent size, right? Then the eigenvalue must not have been too big. Okay. So effectively what this is saying is if I grab eigenvectors with small eigenvalue, most of the energy must have been concentrated in the manifold direction. Okay. So again, this is not a perfect bound. We were not able to perfectly incorporate this into like stability results for this Lego algorithm. That's actually a really cool direction I'd love to go into. This is more just a motivation for that heuristic that I was saying. Eigenvectors vary along the manifold. Okay. And I want to add one more too, because we approach this in two different ways, right? We approach that this is purely continuous. This has nothing to do with discrete data. This has nothing to do with the way we actually built graphs and took eigenvectors of Laplacians. This is like a pure differential geometry style argument, right? So the continuous eigenvectors satisfy this. But then similarly, what we said was, all right, well, let's think about the finite case. Let's talk about some concentration of how close we get to the real Laplacian, the real manifold Laplacian. So you can consider having some clean data and then some noisy data, which was noised by some Gaussian noise. So this is a little bit different than the tubular, but again, it's a different model, right? You had data, it was nice, clean data with low dimensional structure, and then you added Gaussian noise tolerance. Well, if we make some assumptions about what the noise looks like and the variance of the noise, then it turns out that what you can actually prove is that the Laplacian that you actually work with, like the actual n points Laplacian, random walk Laplacian, concentrates near the Laplacian defined on the clean data. And it concentrates near that at a rate of n to the minus 1. In other words, if we have a lot of points, the Laplacian you're going to get from the noisy data is going to, in Frobenius norm, look almost the same as the Laplacian on the clean data. Now, obviously, we're having the noise get smaller and smaller. I recognize that's the case. This is actually something I want to move past towards the tubular neighborhood theory, but it's actually very hard to do. And also, I'm just going to make a comment, which is that this theorem right here is kind of overkill. Because what I'm about to say only uses this theorem for it's kind of a mallet that I'm using to try to do something that's a lot more fine-grained. Because the last thing we can say is, all right, say we had eigenvectors of the noisy Laplacian, eigenvectors of the clean Laplacian. For the first few eigenvectors, all right, m much less than the total number of eigenvectors. As long as the eigenvalues had a little bit of a spectral gap on the order of n to the minus 1/2, which is a pretty reasonable assumption, then the eigenvectors of the low frequency eigenvectors of the noisy Laplacian and the low frequency eigenvectors of the clean Laplacian are effectively the same. This is only true for the low frequency eigenvectors. If m gets anywhere close to n or even square root of n, this theorem breaks down. So really what we're saying is we're using the top theorem to be able to say the first few eigenvectors of that noisy Laplacian really look like the eigenvectors of the clean Laplacian. So they're not varying in the noise direction. They're only varying along the clean direction. Okay. Yeah, so these are two different approaches we take. Like I said, all of the proofs are in the paper itself, but it's basically two different perspectives, both trying to justify rigorously that low frequency eigenvectors in this noisy data regime really do kind of ignore the noise. Okay. All right. So given these two things, let's talk about this whole algorithm together. Right. So what do? Right? We take low frequency eigenvectors, we use them to estimate gradients of the eigenvectors, and then we do PCA of those gradients. So same problem. This is the clean data. This is the local PCA data using 14 nearest neighbors. This is the Lego data also using 14 nearest neighbors. Like I built the exact same graph. I just did something different with it. Right. And what you'll see is that regardless of being in the high noise or low noise region, you're picking up the correct gradient directions. Okay. So again, the image to keep in mind here, right, is that the thing I'm doing PCA of locally in some high noise region are just a bunch of functions that vary only in one direction. So I'm going to ignore the noise when I do PCA of that. Okay. This is the same thing, but what I'm looking at here is actually like the local discrepancy between the tangent vector, the true tangent vector, and my estimated tangent vector. So in this setting, you can see that whenever you're in a high noise region, the estimates are horrible. When you're doing local PCA, when you're in a low noise region, they're good. For Lego, they're just good. There's a couple points right at the worst points of curvature right on the boundary where we don't get perfect estimates. But in general, you're getting a really, really good estimate of the tangent direction. Another example like this, you can do this for the Swiss roll. You can look at the discrepancies. And again, you get much, much lower discrepancies with, again, the same number of nearest neighbors. Okay. And one thing I should say, these are these embeddings I was describing. I'll tell you how we create these embeddings a little bit later. Just this is to say you get good embeddings using this Lego method. You don't get good embeddings using local PCA when your data is noisy. But this plot on the right is, I think, the one that's really interesting. It's the functional variance explained by each principal direction, right? So if you just take your nearest neighbors and you do PCA of that, here's the distribution of your first eigenvalue. Here's the distribution of your second eigenvalue. Here's the distribution of your third eigenvalue. Well, in this problem, it really should only be two-dimensional, right? But you're seeing that you're getting a very significant contribution from the third eigenvalue in the local PCA. But if you look at the gradients and you do SVD of this, it's a rank 2 matrix. There's almost no contribution from the remaining standard values. Okay. And one more example that I just kind of like, this is an example a friend of mine created a long time ago, Roy Lederman, Ronan Tellman. They had this video of these two objects that are rotating, right? So it's a Yoda spinning around and a bulldog spinning around at a different angular speed such that the two are not multiples of each other, so that you're arcing out a torus when this happens. If you took the collection of all of the images, it's creating a torus, 2D torus. So this was the original data. We just played around with it by adding a ton of noise, right? So this is tubular noise, but a lot, right? And we worked purely with the noisy images. So first off, given just a ton of noisy images, you could just do global PCA. If you do global PCA just to reduce the dimension, you see, this is not a fully high dimensional problem. Like there is decay. And if you try to do some PCA embedding, you'd see that like there's some sort of shape here, right? But if you try to refine it, and you try to do like a really good embedding of this 2D torus. Using local PCA, you're going to get a lot of noise, right? And using this Lego, what we can do is we can get an almost perfect embedding of the 2D torus. Okay, now there's a caveat here that I haven't added, which is that we're tearing apart the torus at the boundaries. That's something I'll talk about in a minute. That's part of the manifold learning algorithm. But you can see that using this Lego, you can basically perfectly recover what the geometry was. And I'm showing the clean images here, but this was done on the noisy data. You can see that in this embedding, points that are close to each other are points that more or less should be close to each other, right? This is where the bulldog pretty much isn't moving and the Yoda is rotating. This is where the bulldog is rotating and the Yoda is basically not moving. We're getting a nice embedding from this incredibly noisy set of images because we get really, really good estimates of the local tangent space. Okay. And again, here's the variance explained. Local PCA, it's estimating it's a 9-10 dimensional object. With Lego, almost all of the energy is concentrated in the first two singular values of the gradients. Okay. So this is the summary of the local views, right? We're getting this nice embedding using PCA of the gradients of eigenvectors, the estimates of gradients. Really makes you robust to noise relative to just doing it with PCA. Okay, and this is the paper under review at, I don't even remember at the moment now that I say that. I want to say Science of Data Science. I don't remember off the top of my head. Yeah, it's a pretty fun result. Something we're really excited about. And I think there's a lot of applications outside of just manifold learning. Okay. So that's going to be this first part, this local view. And then if it's okay, I'm going to move on to the global view part. How do we take these and piece them together? Okay. Cool. All right. So now what do we have? Oh, yeah. Question. Oh, okay. So now what do we have? We have a bunch of really good low distortion estimates of our manifold, a bunch of little patches. And we have a way to embed into those patches. But we don't have a global embedding. So how do we do that? How do we align these local views in order to actually create something that's going to have good distortion bands? Okay, so how we do that is through the following. There's a relationship between the patches, right? So for every point, there's a point, and it's also associated with some collection of patches or some collection of views, right? So one point might be seen by several views, right? It's close to a lot of different points, so it's in a bunch of different patches. So what you can do is you can create a bipartite graph, which is basically all points and all views. You have points pointing to views, views pointing to all the points that are in that view. And you get this nice relationship, which is, all right, this is the kth point in the ith view. That's its coordinate. Okay. And now what we want to do is we want to align all of these. Well, the way to align them is that you're allowed to rotate your views, because how you laid down the coordinates, used some principal vectors here, some other principal vectors here. There's no reason that these should agree with each other. Even up to parity, they might just not agree. So you're allowed to rotate your embedding and flip and any orthogonal transformation. And you're allowed to shift them around, right? And what we want to do is we want to shift around our patches and flip around our patches such that if the kth point is in the ith view and the kth point is also in the jth view, you want those coordinates to agree with each other. You want that energy to be small, right? You want to lay it, you want to points that are the same point in two different views better be embedded in the same place. So you want to minimize this object. And I'll just comment that there's an equivalent way to write this down, which is that you create an auxiliary variable, which is your true embedding that you're going to try to learn, and then just make sure you always line up with that true embedding. This is an equivalent optimization. Okay. But what do you want to do? How are you allowed to move your patches around, right? Well, you could have rigid transformations, which is you could do any orthogonal transformation. Or you could have like an affine transformation, which would just be, what you normally get from any kind of, Laplacian eigenmaps or things like this, right? So in the affine assignment, you're trying to find your true embedding Y such that it's a set of orthogonal coordinates. In the rigid transformation, you're doing something much harder. You're trying to treat each SI as a member of the orthogonal group and then solve this very complicated optimization scheme, which quite frankly, the affine is solvable easily. The rigid is NP hard, right? But the affine is not sufficient. Okay, I'll show you why. So here's just a quick example. So you had no noise of a Swiss roll, and you get a bunch of local views, and then you want to align them under affine alignment, right? In other words, find the embedding by looking at like eigenvectors of some matrix. Well, first off, you lose the aspect ratio of your data because you're forcing them to all be, you're forcing all your vectors to be orthonormal. So they're all going to vary the same amount, and you've lost the aspect ratio completely. If you do rigid alignment, you won't have lost that. But then once you add noise, you could also you have a lot of low stability with respect to noise. You're going to have a lot of issues where you get multiple eigenfunctions that vary in the same way. Everything's going to collapse on itself. You get horrible embeddings. If you're doing rigid alignment, things actually are maintained, and you can get really, really nice embedding. Okay, so rigid alignment is where we want to go. The question is, how do we get there, right? So we want to solve this problem, which is the minimum over all orthogonal group over all views of the trace of CSS transpose, where C is just some transformation of the bipartite Laplacian. And there's a million ways to solve this. You can do generalized Bershoot's analysis. You can do Riemannian gradient descent, spectral relaxation, semi-definite programming, generalized power method. We're going to focus on Riemannian gradient descent. And the reason is it's really fast, right? You're optimizing over a manifold here, right? Orthogonal group to the M. That is some very complicated manifold. You're optimizing over it. So Riemannian gradient descent is really going to get you the fastest way to get it. And so what we have here is a series of results that we can set up. I'm actually going to skip this for the sake of time. I'm going to get to this one. So what do we want to do? Well, what we can establish is the following, right? Say you had some, I'm going to call it non-degenerate alignment for the sake of this. Just say you have a nice alignment. Then there exists some radius, okay, such that if you initialized at S0 and your goal was to reach S is unknown, right? So S is my critical point. I initialize at S0. I want to reach S. As long as I am within some radius of convergence, then RGD actually converges linearly. So you get incredibly fast convergence. And we can explicitly write down what this radius convergence is in terms of a whole bunch of different Laplacians and matrices and Kronecker products and matrices and eigenvalues. And there's a lot of technical, subtext to a lot of this. But the point is that this can be explicitly characterized. Okay. So what this says is as long as we lay down our patches in such a way that we had a decent estimate, then RGD will get us a really good estimate really, really fast. So how do we get a decent estimate? So how we get a decent estimate is that we initialize with a spectral embedding. So this is a setting where we have local views, we have noise on our local views, and what we're going to do is we're going to use some initial spectral alignment. So we had all these patches. We solve a spectral alignment first that lines them up decently. We can bound the definition of decent. Okay, this is an upper bound on how much error you have from the spectral bound. As long as that is less than the radius of convergence, then we're golden. Right? So what do? You take all your patches, you solve a quick spectral problem to get a decent estimate. As long as the decent estimate is within that radius of convergence, then you run Riemannian gradient descent, boom, you get a perfect embedding. Okay. And so what this is saying is that like we have a decent way to estimate our initial laydown of where the patches are, and then from that, Riemannian gradient descent will give us a really, really good estimate of our global geometry. Okay. And by the way, it runs really fast. So this is just an initial example. You initially lay the patches down somehow, run RGD, boom, you get this really nice estimate of like a high aspect ratio rectangle, right? Global Pursuits isn't as good. Or global power method isn't as good. Pursuits isn't as good. Spectral is okay, but not as good. Semi-definite programming is okay, not as good. This is how long all of these things take. RGD is the one in blue. Boom, you decay incredibly fast, right? So once you have that initialization, you're going to get a very, very fast convergence to a really, really good alignment. Okay. For the sake of time, I'm going to skip over this. This has to do with all the different notions of alignment, which, quite frankly, I don't want to go into at the moment. But it is a part of this paper. For the sake of time, I'm going to skip it. But basically, yeah, non-degenerate rigid alignment. If you're interested, there's a lot of very cool Riemannian gradient descent analysis here of basically showing that, under certain settings, you have a non-degenerate minimum, and that means that you're going to get fast convergence of RGD, and how do you know you're in the neighborhood and things like this. But I want to add one more component to this, which I think is important, and that is the fact that in a lot of these manifolds, there's no boundary, right? So for example, just take something as simple as a circle. There's no way to embed a circle in 1D and not have distortion, right? No matter how you do it, you're going to collapse points on top of each other. But we as mathematicians have thought about how to do this for a long time, right? How do you draw a torus? How do you draw a circle in 1D? You cut somewhere, and then you assign gluing instructions, right? So you cut, and then you lay it down on a 1D line, and you just write down some mechanism by which you say, all right, once you leave this point over here on the right, you re-enter at this point over here on the left, right? That's how we write down a torus in 1D. So what we're going to do is actually that, right? We're actually going to sort of do that computationally, right? So what we do is we have this really good estimate of this bipartite graph. How are all views related to all other views? And we're laying them all down. But the problem is, if you're trying to embed a sphere, there's no way to do it, right? Like there's no way to actually embed a sphere into 2 dimensions that would have low distortion. So what we do is a tree-based alignment, which is basically we lay down a very popular view, and then we lay down its neighboring views, lay down its neighboring views. And after a while, you might run into a pathology. And that pathology is, oh, I laid down a view over here that should be connected to something, way over here. And so we store that. We know they should be connected, but we effectively just say to the algorithm, like, all right, ignore that, right? You tear apart that edge. Okay. But you know where it should have been connected, right? This view should have been connected to this view, so on and so on. And this is our initial overtorn embedding. And then you stitch it back via Riemannian gradient descent. And you get a really nice smooth embedding of the sphere, along with the gluing instructions. And here I'm just coloring them by color, but like you see that like the red should be glued to the red, the light red to the light red, the dark blue to the dark blue, the light blue to the light blue. And you can imagine if you rotated that back over on itself, it would look like a sphere again. Okay. So one other thing to mention about this is the distortion we get from all of this. Okay. So now we have nice estimates of local views. We have ways to lay down all of our patches originally. We have ways to do Riemannian gradient descent to align our patches. Now we need to measure the quality of this. Okay, so how do we do that? Well, best thing to measure with is local distortion. So local distortion is basically how far apart are 2 points in your embedding divided by how far apart they were in the original space. And then you take the worst of that, and then you take the minimum of this, and you look at the ratio of those 2 quantities, and this is the condition number of your embedding, right? 1, perfect, infinite means something got ripped apart or 2 things got collapsed on top of each other. We just want a finite distortion embedding. That's all. And so it turns out there's two different notions of distortion that are nice. One is called strong distortion. Strong distortion says take 2 points in our original space, take 2 points in our embedding. Look at the distance between those 2 points in the original space. Look at the distance between those 2 points in the embedding space. Okay. You take a max of that ratio, you take a min of the ratio, divide, and that's called strong distortion. It's telling you like how much have you ripped or squashed your embedding globally. Okay. And then there's another notion called weak distortion. So weak distortion says I'm going to take 2 points in my output space, in my data space, draw a line between them. How big is that line? Now in the low dimensional space, I'm going to track the exact same line, the exact same set of points along that path and measure how long that path was. And I'm going to use that as my distance in the embedding space. Okay. And that's called weak distortion. And there's this really fun thing that shows up, which is basically if you have low, strong distortion, you're good. That's the best thing you can get. But if you have high, strong distortion and low, weak distortion, often what that means is you've collapsed your embedding on top of itself. So what we want to see is that strong and weak distortion are kind of on the same scale. That's actually going to be the best measure we can get. Okay. And so we have a few statements that can be made that actually can bound the global distortion of our embedding. So this is the weak distortion. So this is going to be our worst weak distortion. Okay. And it's bounded by a few quantities that I'm going to highlight here, but basically it has to do with kappa is kind of the distortion of my local views. If I had horrible local views, I'm never going to get better, right? So Lego gives us nice local views. That's great. This GS over here is a quantity that is actually related to the alignment error, the thing we are optimizing, right? And then G2 is also related to the thing we are optimizing. So what this says is, if my local views are good, and if I can make this FS small, then my weak distortion is small. So every step I take of Riemannian gradient descent to make this FS smaller makes the weak distortion smaller. That's awesome, right? But it's not the strong distortion, right? Oh, and by the way, I should just say, if you have perfect local views and you have perfect alignment, then you have a perfect bound on the weak distortion. It's basically just related to the curvature of your manifold. Okay. But for strong distortion, it's a little bit harder. You need to have an additional assumption. The assumption is that neighbors in your embedding space are also neighbors in your data space. And if you make that assumption, you can get this really like the equivalent bound, basically. So how do you do this? Well, how we do this is we just add a small repulsion term. So what that repulsion term does is it says, all right, if 2 points were really far apart in the data space, keep them far apart in the embedding space. So we create a slightly different optimization scheme. It's this alignment error I was already talking about, and then this penalization. And it turns out you can rewrite this as this nice semi-definite programming type problem for a particular matrix C, which it turns out this whole thing in here is actually just going to be, it's a combinatorial Laplacian of a signed graph. So basically you keep track of what views you want to strengthen, and also what views you want to repel. That creates a signed graph, and then all of the theory I described before still applies. You can still optimize quickly, you can still reach global minimum. And now what you have is an embedding that not just tries to align your views as best as possible, but says if two views are far apart from each other, keep them far apart. Okay, and that makes sure that that bound we had for weak distortion will also apply to strong distortion. Okay. So for the sake of time, I'm going to skip a couple of slides here because I want to get to the main, the applications. So this is the paper for Attaining repulsion enabled registration. Yeah, so we have this whole pipeline now, right? This pipeline says you take your data, You get nice local views using Lego. You lay them all down in some sort of tree-based structure, right? And you initialize with some sort of spectral method to get like an initial estimate of what the local view layout should look like. And now we run Riemannian gradient descent, where we try to pull patches together, but also make sure that if patches are far apart, you keep them far apart. Okay, that's the pipeline. That's the full algorithm in totality of a bottom-up manifold learning algorithm. So let's talk about how this actually works. How does the distortion created impact downstream performance? Does the fact that we have finite distortion help us? So let's look at a few examples. So here's my first one. So this is actually, you take neuronal activity from mice, and you're just looking at their head orientation as they move it around. Okay. And in this setting, they're basically just rotating their head. You should just be arcing out something that's effectively a circle. Okay. But the neuron, you're collecting a lot of neurons, which means it's high dimensional data, and you want to get a low dimensional embed. So, here's PCA of your data. You originally had 22 neurons you were measuring. You do PCA, you get something that's all collapsed on top of itself. You do TS&E, you get a circle, LTSA, UMAP, isomap. With rats, we're able to rip things apart. We're able to say like, oh, that patch and that patch, they should have been connected. That's going to lead to some sort of weird pathology. Let's keep them apart and just remember one patch cannot map to the other. And what you get is a perfect embedding into one intrinsic dimension, straight line. It mirrors incredibly closely the angle of the head. Okay. Let's go to something a little bit more fun, a little bit harder, which is a monkey that's actually, again, you're collecting neurons, 74 input, and there's 2 degrees of freedom here. There's they're cranking a wheel to move something on a video. So the first thing is, what's the angle that their hand is at? And the second is, how fast are they going? Okay, those are the 2 objects you're trying to collect from the neurons, right? And this was done in let's call it a supervised way, where neuroscientists know which neurons to measure in order to collect those pieces of information, right? But this is 74-dimensional data across time. You do a TS&E of it, you get things that look like this. UMAP, isomap. With rats, what we wind up getting, sorry, rats is, what is it? Riemannian aligned tangent spaces. Yeah. With rats, what you wind up getting is this nice 2D embedding where along one direction, what you're measuring is the angle. So at one side, the angle is basically 0. At the other side, the angle is like 2 pi. Okay. And then it loops back on itself. And equivalently, then the color is how fast the monkey is spinning the wheel. This is done completely unsupervised. This is an unsupervised embedding. And what we're learning is that we can actually see this rigid 2-dimensional structure, which is that the speed that they're going is effectively orthogonal to the angle that they're thinking, right? And so if you want to see, the neuronal structure when the hand went slower, you just kind of move down this embedding. Faster, you move up the embedding. And you can even do something like decoding the angle. What angle was their hand at? You can look at, a coordinate system along one of these little wisps and look at its correlation with the actual angle, the known angle that their hand was at. And you see that you have an almost linear relationship. This is across a whole bunch of different experiments. Okay. So you really are getting like, okay, my coordinates are moving linearly with respect to the angle. And then one more I'll add, and then I'm done. You have mice moving around in some 2D field, and there are actually a lot of neurons that measure, they call it like grid cells. So basically, it's firings in the brain that kind of help the mouse orient themselves with where they are in the space. Okay. So you take high dimensional data, you do PCA of it, and then you want to lay it down into 2 dimensions. You can't with any of the other methods. You get 3 dimensions. There's a lot of distortion. Weird things happen with rats. 2-dimensional embedding. It is a 2D torus. You can see that quite clearly in the embedding structure. Right. And then you can do downstream tasks like ask, is this truly a 2D torus? And you could run some sort of persistence homology and get very clearly that it is. Right. And this has to do with the ratio of the lifetimes of the persistence bars. Basically, RATS is a much more stable TDA analysis. Gives you a much more stable TDA analysis down. So that's the idea. These are just a few applications, but I just kind of want to give a summary, right? So bottom up, you're guaranteed to have local views with finite distortion. You're guaranteed to patch them together with finite distortion. And then as you optimize, the distortion gets better and better. So that's already something that's pretty nice. Um, yeah, and there's some really fun mathematics here. There's mathematics about Riemannian gradient descent, mathematics about, local tangent spaces, about gradient eigenvectors of gradients. And there's still a lot of open questions. I mean, what I'm saying here is basically I'm showing you some informal theorems. Um, there's still a lot of open questions about piecing some of the different parts together, right? And there's a ton of directions that I really want to go, right? Embeddings that maintain temporal behavior, right? We're treating time as just like irrelevant, right? We're just every point is a point regardless of the time we sampled it. Multimodal task-based learning. This can get into some really fun stuff about like average gradient outer product matrices and how to identify what neurons are actually driving a task in a supervised way, and then trying to get some sort of low dimensional embedding just of the neurons relevant to the task. Yeah, and a bunch of others. So that's the talk. Thanks.